to The Explainer. Today, we're diving deep into an invisible force that's all around us. One that powers stars, keeps our planet's core molten, and even lets us peer back in time. We're talking about radioactive decay. All right, so let's start with a kind of surprising idea. Not everything in the universe is built to last forever. I mean, way down at the atomic level, some of the universe's basic building blocks are fundamentally unstable. They're just packed with way too much energy for their own good. So what if the atoms that make up, well, everything, actually, had an expiration date? What if they were designed to just spontaneously change? You know, it might sound like total chaos, but it's actually one of the most fundamental and surprisingly orderly processes in the entire universe. And that's exactly what radioactive decay is. It's the process where an unstable atom just sheds that extra energy as radiation, and in doing so, it transforms itself into something more stable. You can think of it as nature's way of just settling down, getting into a more comfortable, lower energy state. Now, when this happens, we call the original nucleus the parent, and what it turns into are the daughter products. And listen, this isn't some minor tweak. This decay can literally be a nuclear transmutation, often creating a completely new element with a different number of protons. It's atomic alchemy. So the big question is, how exactly does this energy get released? Well, it turns out there are three main ways this happens, which gives us three very distinct characters in the whole story of decay. And what's so fascinating when you look at this is just how different they are from each other. Alpha particles, they're the heavy hitters. They're basically a whole helium nucleus, 2 protons and 2 neutrons. Then you've got beta particles, which are these nimble, high-speed electrons. And gamma rays, they aren't particles at all. They're just pure, high-energy electromagnetic radiation. And this right here, this shows you their distinct personalities perfectly. Because alpha particles are so big and clunky, they can be stopped by something as simple as a sheet of paper, or even just the outer layer of your skin. Beta particles, they're a bit more persistent. You'll need a thin sheet of aluminum to stop them. But gamma rays, being pure energy, they're the real escape artists. They're the most penetrating, and you need thick, dense stuff like lead to even begin to shield against them. Okay, this brings us to a really fascinating paradox. If the decay of any single atom is completely random and unpredictable, how in the world can we use it for anything predictable? How do you get a clock out of pure chaos? Yeah, it definitely seems like a contradiction. But the answer, it turns out, lies in the incredible power of large numbers. So according to quantum theory, you can never ever predict when one specific atom is going to decay. But when you have billions and billions of them all together, a really clear pattern starts to emerge. So while you can't tell me which atom is going to decay next, you can predict with incredible accuracy how long it'll take for half of a whole group of them to decay. It's this statistical certainty that we call the half-life. Let's take carbon-14, for example. You've probably heard of it. It's a huge deal for archaeologists. Its half-life is about 5,700 years. So what that means is, if you had a chunk of it today, in 5,700 years, exactly half of it would be gone. Then after another 5,700 years, half of that remainder would be gone, and so on, just ticking away with this incredible regularity. And that predictability, that unwavering statistical clock, is what lets us measure the age of, well, almost anything, from ancient artifacts and fossils to the geological formations of our planet itself. It's incredible. But, humanity's journey to understanding this whole process, it wasn't exactly a straight line. It was filled with brilliant, mind-blowing discoveries, but also with unforeseen and often really tragic danger. And the crazy thing is how fast it all happened. It all started by accident, really, in 1896. Henri Becquerel noticed these mysterious rays from uranium salts had fogged up a photographic plate. Just 2 years later, Marie and Pierre Curie isolate 2 totally new elements, polonium and radium. And they give this phenomenon its name, radioactivity. Then, in 1902, Ernest Rutherford makes the final conceptual leap, realizing that these atoms were literally transforming into other elements. I mean, that's a revolution in physics, all in just 6 years. But here's the thing, the dangers of this powerful new force were not understood at all. Early researchers were reporting things like burns and hair loss. Even worse, radioactive substances were actually marketed as miracle cures. You could buy radium enema treatments and tonics that you were supposed to drink. This whole period of radioactive quackery, it had tragic consequences, including for Marie Curie herself, whose death was almost certainly caused by her lifelong exposure. And Marie Curie, she saw what was happening. She pleaded against this reckless commercialization of it all, warning everyone that the power they'd unlocked was not a toy. Her words, "Radium is dangerous in untrained hands," became a tragic and powerful prophecy. So, after this pretty terrifying start, how did we finally learn to harness this unstable atomic heart for good? How did we manage to turn this mysterious, dangerous force into a precision tool? Well, today, we use the principles of decay in countless ways. Radiometric dating is literally our window into the deep past. In medicine, we use something called radioisotopic labeling to trace chemicals through the human body and diagnose diseases. And on a planetary scale, the slow, steady decay of elements deep within the Earth is a primary source of the heat that drives our geology and keeps our planet's core molten. So from a mysterious glow on a photographic plate to the very engine of our planet, the story of radioactive decay shows us this powerful, predictable order that's hidden inside instability. The fact that atoms fall apart is precisely what gives us the power to piece our world's history together. It really makes you wonder, doesn't it? What else might the instability of matter reveal?